All right, let's finish up torque. Now, we mentioned it briefly in the last example of the notes from yesterday. When you have a net torque of zero, that's when we have a state of what we call rotational equilibrium. All right, so with translational equilibrium, right, which we covered first semester, right, a net force of zero means that your object is not accelerating, meaning that you have something that's traveling at a constant speed or it's not moving. It's the same thing with rotational equilibrium. If your net torque is zero, well, in those cases, your object is either rotating at a constant speed or it's not rotating at all. So let's take a look at the example in the notes. So we've got a boy of mass 30 kilograms. He wishes to play on a centrally pivoted seesaw with his dog Irving, who has a mass of 10 kilograms. When the dog sits 3 meters from the pivot, we want to know where the boy must sit if the 6.5 meter long board is to be balanced horizontally. So let's start by just setting this up. Now we've got ourselves a seesaw with a centrally located pivot. Now we've got our dog, Irving, who is sitting 3 meters from the pivot. So we can call this distance Ri for Irving. And that is 3 meters. And we want to know where the boy needs to be sitting in order to balance this out. So RB, the distance of the boy, is going to be our what we're looking for. Now keep in mind these distances, right? They're all measured from that pivot point. So anytime you are plugging in an R in your torque equation, keep in mind that one of the points that you're measuring from has to be the pivot point. Now, we know that the dog has some force of gravity acting downwards. And the boy also has weight. And so these two forces are what's going to be exerting torque on the seesaw itself. So in the boy's case, his weight, we'll call it torque boy, would be generating a clockwise torque. The dog, his weight, would be generating a counterclockwise torque. Now, if this seesaw is balanced, then we know that the net torque has to be equal to zero. Right? Your clockwise torque has to equal your counterclockwise torque. So we know that the torque generated by Irving has to equal the torque generated by the boy. So the force responsible for the torque generated by Irving is Irving's weight, right? So the mass of Irving times G times Irving's distance from the pivot point, right, is equal to the weight of the boy. So the mass of the boy times G times the boy's distance from the pivot point. Notice we can cancel out G here. So it really doesn't matter what planet the seesaw is on. Either way, the boy has to be a certain distance away. And so we know that the mass of the dog is 10 kilograms, and he sits 3 meters away. We know the boy has a mass of 30 kilograms, sitting at an unknown distance. Alright, so you solve it out. 30 divided by 30. The boy needs to be 1 meter away from the pivot point on that seesaw. Alright, so again, the key idea here is that when you have net torque equal to zero, it means that your total counterclockwise torque has to equal your total clockwise torque. So now let's quickly look at center of gravity. Now, when we're talking about the center of gravity, what we're talking about is a point on an object where we can imagine all of the weight of that object to be acting. So, in the notes, for instance, we have this image of a gymnast. Now, obviously, each particle that makes up the gymnast, right, exerts a torque due to the weight of that particle. But it's impractical to consider each individual point of a complex object, right? So instead, what we can do is we can imagine that all of the weight scattered throughout, the ununiformly distributed particles of this gymnast to be acting in one place that we call the center of gravity, right? So that way we can actually take into account an object's weight in causing rotations. So, for instance, if we're looking at a uniform meter stick, for instance, now a meter stick, right, is 1 meter long. If it's uniform, that means that all of its weight is going to be distributed equally throughout. So, if we want to know what the center of gravity of that meter stick is, well, the center of gravity, so we'll say COG, is going to be at the 50 centimeter mark of that meter stick. And so the reason this matters is, let's say we're doing a lab and we've got a meter stick, and let's say we set the pivot point of that meter stick here at, let's say, 30 centimeters. Well, what's going to happen to that meter stick? That meter stick, right, is going to swing this direction. Well, why is that? Right? We haven't attached any masses on either end. Well, it's because at the 50 centimeter mark, so right here, you have the mass of the meter stick times the gravitational acceleration, right, exerting a force to cause it to rotate. Now, same thing if we move the pivot onto the other side, right? Your torque would be just counterclockwise instead of clockwise. And again, it would be rotating due to the weight of the meter stick itself. Now, what if, though, in this experiment, we put the pivot directly at 50 centimeters? Well, in that case, right, the weight of the meter stick is pushing directly on the pivot. So it's just like pulling directly outwards on the door or pushing directly inwards on the door towards or away from the hinge, right? That door is never going to rotate if you're directing your force parallel to the hinge itself. And so in that case, right, your torque here, if it's equal to force times r perpendicular, well, r is 0. Right, so no torque is generated. And so that's why in the last problem with the boy and its dog on the seesaw, we didn't have to take into account the weight of the seesaw itself generating any torque, because that pivot point on a seesaw is located centrally, and we consider the seesaw to be uniform. So the center of gravity is negated based off of there being no distance from the pivot itself, right? The center of gravity of the seesaw is directly on top of your pivot point. So let's take a look at this in action. So in example 712 in the notes, we got a 3.2 kilogram flagpole. It extends from the wall at an angle of 25 degrees from the horizontal. Its center of gravity is 1.6 meters from the point where the pole is attached to the wall. What is the gravitational torque on the flagpole about the point of attachment? So first off, they've done us a favor and drawn all this out. Now notice, they've drawn the line of action, meaning that they've extended that vector into infinity. And so, if we're looking for the torque, we need to find the moment arm, meaning a direct line from the pivot, which in this case would be right here at the wall, that intersects with that line of action at a 90-degree angle. So, if we know that r, the distance to the center of mass, is 1.6 meters, and we know that it is at a 25-degree angle, right? We can find the moment arm. So our moment arm is going to be equal to r times the cosine of 25 degrees. So r perpendicular, your moment arm, is 1.6 meters times the cosine of 25. Again, make sure that you are in degrees and not radians. And that comes out to 1.45 meters. So, again, if this is the center of gravity, right, we know that we are looking at the weight of the flagpole that is generating a clockwise torque. So our torque is equal to our force times our moment arm. So the torque is equal to mg times r perpendicular. So the torque would be, see, it's the mass, 3.2 kilograms, times 9.8 meters per second squared, times 1.45 meters, which gives us a torque of 45.5 Newton meters. Since it's clockwise, it'd be negative. And there we go. So in the next video, probably posting next week, we're going to spend quite a bit of time on torque because torque is generally what most people have issues with. We will start with rotational inertia, and that will be followed by rotational momentum, and then that is all for new material. So just make sure you guys are keeping up and come and ask questions when you have them. Yeah, I will see you guys soon.